Okay. Alright, so how's everyone doing? I'll take your silence as good. Okay, that's good you're alive. At first I thought, Christopher, I thought you said dad. I was very confused. Okay, so today, got a few things. We got the lecture for the third lab, but more importantly, some announcements. Your first memo is due today, so it's due by 11:59 p.m., so make sure that you turn that in on time. I see there's only 3 of you that turned it in so far. I mean, technically, that's fine. Just make sure you turn it in on time. And let's see. So I got a few questions on the data sheets that you should include. Okay, so if you're in the syllabus and you look at the different sections in the appendix, one of the things that you should include is the data sheet. And, you know, for your experiment, I think you have like 400 rows per test. That's kind of ridiculous, right? So for this experiment, you can just include like 5 to 10 rows of data for each test, and that's okay. I mean, it's not a great solution, but having like 400 rows of data, you know, in your memo is just insane. So don't do that. Okay, and let's see. Let's go here. So just a few more reminders too for the memo. Take a look at this abstract resource if you haven't already. That'll help you write the abstract. Should be about 200 words long, or 250 is really the high end, but for this lab, you should be able to write your abstract within 200 words. So take a look at that. And then there's also this memo template. So you can take a look at this too to see how your memo should kind of look. You know, you can have your own style, of course, but it should look something like this. Okay, so you can kind of see the format, and I also just kind of go into more depth for what each section should have. Although, I guess I forgot to put a references section in here, so my bad. But if you go on the syllabus and you look at all of the rubric I have that you just saw, there's a section for references. So you need to make sure that you have references. And so yeah, so take a look at that. I'm gonna pull up a past student's memo really quick here to show how the references should look both at the end of the document and then also in text. Yeah, Amra, yeah, you include the entire MATLAB script in your appendix section as well. All right, so if you look at this past student's memo, did I go to the right one? Okay, there we go. Okay, so if you look at this student's memo, you know, we're looking here at the results section. So they have their elastic modulus, the yield strength, tensile strength, and they also have the fracture point. You don't need to include that though. But basically what I want to show you is they have their sources, you know, they have an in-text citation here for the published values. And then towards the end of their document, they have a references section here. Where is it? Here. Okay, so you got a full page here for references, and it's referring to that in-text citation that they had earlier on. So just to show you what that should look like for your report. Okay, and let's see, before we move on, are there any questions for your memo that's due today? Close out of this.
I have a question. How did you
Yeah.
publish your code like that?
Hold on. Let me get my camera back. Oh, I didn't mean to open up MATLAB. So yeah, the code, how I have it formatted, I wrote this document in LaTeX. So there's a package add-on in LaTeX to have it formatted like this. So if you do it in Word, and it's a bit different. I don't know the best method for Word, to be honest. I think you can just copy and paste it, but I don't think it's gonna save the formatting. So I don't really have a good answer for Word.
All right, thank you.
Okay. Why did it close out of everything? Okay, question. How detailed should the references be? And do we need to include pictures from the lab? So the references should be like I just showed you from that example for that student. It's not like too in depth. I mean, you just need to have it in text, number one, and then at the end it should be like the title of the web page that you're looking at, and then the website. Okay, and then a few more things. Memo 2, I uploaded a video for that, so you can check that out. There's two different videos. So one of them is using MATLAB, and another is using Python. Okay, so, I said that MATLAB is required in this class, right? But really, you can use other programming languages as well if you want. So the MATLAB one is here. No, the MATLAB one is here. And then the Python one, it has Python in the title, so you can check that out. I would just recommend that, just in general, to kind of dip your toes into other programming languages like Python, just because Python is used way more outside of school than MATLAB. MATLAB is hardly ever used. So, anyways, that's optional. You can just look at that video if you want to take a look, and you'll see that it's pretty similar to MATLAB though. And another thing for the second production stayed in there. There was an error that I had in that video, which was calculating area. I messed up my parentheses. So, um, well, it says it in the description for the video, but I basically messed up the parentheses at one point in the video when I was calculating the cross-sectional area. In the description of the video, I show the correct formatting. And then the last thing is group names. So I think there's one more group where I need your group names class. So if you guys haven't made a group name for your group yet, make that today and then let me know what your group name is. And in Discord, I'm organizing everything by group. Alright, so before we get started on the lecture, are there any questions on the first memo or the second memo? Second memo is due next week, by the way. Okay. All right, so let's check out VKS. So we're gonna be doing a lecture on the third lab, which is for the beam. So the beam is going to be different kind of loading than we had in the first two labs. Okay, so the first two labs we had a tensile loading, and this lab we're going to have a transverse loading on a beam, and that's going to cause bending to occur and deflection. So this is the beam that we have. It's an I-beam using 1018 steel. And also on here, it's going to be on the bottom surface. We have a strain gauge. And that's being used to, well, of course, measure the strain. But later on, we're going to use that strain value and we're going to use it to calculate the bending stress that's occurring on this surface here. Okay, so here is what the cross section looks like for the I-beam. Wow, it looks like an eye. So once you actually get into the lab, you're going to get a sample and you're going to measure these different dimensions of the I-beam. Here's the test setup. It obviously looks different than the first two labs. Okay, got your two roller supports there. So here's the strain gauge on the bottom. And then we're also going to measure the vertical deflection. So we have this dial gauge here. There's an updated one in the lab now. It's a fully digital dial gauge, so it doesn't look old like this. And this is just kind of, I don't know, a little fussy to use. So anyways, there's going to be this indicator that's under the beam, and it's going to be directly in the center because that's where the maximum deflection is going to occur. We'll talk about that. And you're gonna, again, just have a dial gauge, a digital one, and you're just going to read out the deflection. So this should also be set up for you automatically. Well, the lab technician will set it up. And you should check though, once you're in the lab, you'll see this black line here. The dial gauge should be aligned with that. Okay, so that's a little preview of what the lab is going to look like. Okay, now we'll do the lecture. Alright, so again, we have a beam. So let's first define what a beam does. Okay, so a beam is going to support a transverse load. So that's a load that's perpendicular to, I'm gonna hit my mic, it's perpendicular to the longitudinal axis of the beam. And from that load, there's going to be bending stress and then, of course, deflection. Okay, so now I'll make a drawing of what the beam and the loads are going to look like for the lab. I haven't uploaded the handout yet, because there's going to be an updated handout like we've had for the first two labs, because we have new software this semester. Once I get the updated version of the handout, I will upload that to Canvas. Okay, so here we have our beam. And I believe the beam is 12 inches long, but once I get that updated handout, I'll be sure to double check that. And then you'll see that we kind of break the beam up into 3 different sections where they're each 4 inches long. Okay, pretend all of those are even, and each of these sections, they're denoted A. I'm just following the convention from the handout. So again, they're each 4 inches long, and then up top, we have 2 loads here. Really, we're applying one load, but that load is separated off into 2 different kind of structures. So we have P divided by 2 and P divided by 2 on both of those loads. Of course, as we run the test, that load is going to increase. And just like we did for lab 2, we're going to stay within the elastic range for this test. So the software is going to stop it at some point. I forget what that maximum load is offhand, but it's going to increase to a certain point and then it'll stop. So we stay within the elastic range, because we have a strain gauge on there, don't want to break that. And we have it's a pretty substantial little beam for testing purposes. Okay, and then of course, again, the end goal is to apply this load and measure the bending stress and the vertical deflection. So what we're going to do is go through the theory now for how we're going to get the theoretical bending stress and the theoretical vertical deflection. And we're going to compare those values to the experimental bending stress and deflection. Okay, so from this setup here, if you kind of think back to your solid mechanics class, or maybe you're taking that right now, remember your shear and moment diagrams. I'm going to draw the moment diagram here. It's been a while since I've done these. So what you'll have for the moment diagram, it'll look like this, and our maximum moment here is going to be P, which is the load, multiplied by A divided by 2. Well, P divided by 2 is the load, and we multiply that by A, and that's our moment. So in the very center here, in that kind of center section, you see that we have we have just the moment. The moment is constant there. And what that is saying is that we have pure bending in that very middle section. Okay, so right here we have pure bending. So there's no shear force that's present. So that's going to be the area of interest for the lab. Okay, that's where we're going to look at the bending stress and the vertical deflection. Okay, so now we're going to take a little cross section of the beam, and we're going to see how the top surface and the bottom surface and everything in between, how that's going to change once we're applying a load to it. Come on, make a square. Okay, so there we go. Imagine that this is a cross section. And so once you're in your class, your solid mechanics class, and you guys talk about bending, your instructor or professor, they're probably going to go over this and they'll say, imagine that in the beginning, before you apply your load, you have these stacked longitudinal fibers. So, that's not really the case here, but you're going to imagine that there's all of these fibers here that are parallel to one another. All right, and then once we apply the load, we're going to see how these fibers change. So apply our load. In this cross section, we're going to exaggerate it. Okay, it's going to deform, or it's going to deflect. So on the very top surface, all of those fibers that we just had, they're now shortened and compressed. And then everything on the bottom, they are elongated in tension. So it's kind of intuitive. If I go back to my ruler that I keep using, if I apply a load on this, then everything on top that's getting compressed, and everything on the bottom that's going into tension. So this isn't great because there's not much thickness, but everything on that top surface, it's getting squished together in compression. Everything on the bottom, it's getting elongated in tension. And of course, you can think back to the first two labs too. You saw that when we were applying tension, that the rod was elongating, just getting longer. So we have this kind of gradient going from either compression to tension or from tension to compression, which is then implying that there's somewhere in between here where we're neither in compression or in tension. Okay, and that surface is going to be called the neutral surface. All right, so that's in blue. That's the neutral surface, or you might hear it called neutral axis. All right, so that's going to be really important because we use the location of the neutral surface to help us calculate the bending stress. But the neutral surface, it can be kind of hard to find sometimes. But for us, our geometry is pretty simple. It's a symmetric I-beam. And basically after a lot of math, which we're going to skip right now, because it'd be like a page or two, so I'll leave that to your solid mechanics class. But after a lot of math, what you are going to come to is the result that the neutral surface, it's going to pass through the location of the centroid for your object. And again, we have a pretty simple geometry, so we can easily find the centroid of our beam. It's just going to be right in the middle. So then we know where that neutral surface is, and we can calculate the bending stress. I should also add on that this is that result where our neutral surface, it passes through our centroid, that's only valid for pure bending. So that's another reason why we're looking at just that very middle section. Because remember, that middle section here, that's in pure bending. Okay, and again, we know where that centroid is. It's going to be in the very middle of our beam. So we know where it is. That it's going to be h divided by 2, the height divided by 2. Okay, so now that we have this kind of simplification, which is obviously very nice, we can actually now calculate the bending stress. Yeah, it's the centroid at the initial position. Yeah, that's a good point. Because it will be different technically once we start applying stress. Okay, so the basic formula for bending stress, let's write that out. All right, so we have sigma b, the b obviously for bending. That'll be our moment that we have at whatever location we're looking at, multiplied by y, which is going to be the distance from the neutral surface, and then divided by I, the moment of inertia. So again, m is the moment, y is the distance from the neutral surface, I just realized too, I've had my computer muted because Discord kept going off. So hopefully no one asked a question and I ignored you. If that's the case, sorry. I just unmuted it again now. Okay. Again, I, that's the moment of inertia. So we're gonna actually, I'll write out the formula for that at the very end of class and show you how that's calculated. So m, the moment, actually before we do that, let's talk about how now, we have the general formula for bending stress, but for our experiment, we want to find the maximum bending stress. So that maximum bending stress, it's going to occur either on the top surface of our beam or on the bottom surface. Okay, because remember, on the top surface, we're in compression, so there's a lot of stress going on there. And on the bottom surface, that is in tension, so there's going to be a lot of stress there. As we start to go, towards the middle of the beam, we get less and less stress. So, in theory, our beam is perfectly symmetric, so both the top and the bottom surface, they're actually going to have the same amount of stress. Of course, in reality, that's not really the case. It's not going to be perfectly symmetric. But that's why this is the theoretical maximum bending stress. But that'll be something that you should keep in mind for your memo for this report, is that, we're using equations that say, in theory, this is perfectly symmetric, but in reality, it's not. So in the lab, remember that we have the strain gauge on the bottom, and not the top, but to repeat myself again, in theory, both the top and the bottom are going to have the same stress, and that's where the maximum bending stress is going to occur for the beam. Okay, so one of the things that we have to do is obviously calculate where that, or what the theoretical max bending stress is. So we have sigma b theo for theoretical. That's equal to, again, the moment times the distance from the neutral surface divided by I, the moment of inertia. So the moment is P divided by A, P divided by 2 multiplied by A, where A is 4 inches. Okay, we're looking at that middle section there. And then Y, the distance from the neutral surface, is going to be H divided by 2. Okay, because our neutral surface is in the very middle of the beam. So the distance from the neutral surface for either the top or the bottom, in our case, the bottom is going to be the height divided by 2. And then the moment of inertia, we're going to get that formula at the very end. And basically what you'll do in the data reduction is make a variable for all of these. So one for the moment, one for the distance from the neutral surface, and one for the moment of inertia. And then you can plug in all of those variables into sigma b theo to calculate that theoretical bending stress. Okay, so, y, that's going to be constant. It's always going to be h divided by 2 for that distance from the neutral surface. And our moment of inertia, that's going to be constant. So the only thing changing is the moment because our load is changing. Okay, so that's the theoretical version. Now we need the experimental version. Okay, so we have a strain gauge, remember? So we're using that to measure the strain on the bottom surface. So we can use Hooke's law again, because we're staying within the elastic range. And we can get sigma b experimental. That's going to be equal to the elastic modulus for the material 1018 steel. So you can just look at the published value for that. I think I'm posting it this time on the deliverables. And then the strain gauge, that's in units of microstrain. So we're taking that, multiplying them, and then we can get our experimental bending stress that way. Okay, so the next thing is going to be the theoretical vertical deflection. All right, so here we have a formula for this as well. There's not going to be a derivation for this one, so I'm just going to write out the formula. And this almost looks like an empirical equation, but it's not. It is a theoretical equation. So we're going to write this as delta theo. That's going to be equal to 23 times our load times L cubed divided by 1,296 multiplied by the elastic modulus and the moment of inertia. Okay. And so this, remember, we have our beam here. And then once we apply our load, it's going to look, something like that, right? So we want to measure that deflection where it went down. So maybe I should have even exaggerated it more. So we want to measure that deflection right there. And so what we have instead is we actually have, that dial gauge on the bottom, but it's going to measure that change in its position to then measure the deflection. Okay, so that's what we're measuring. And again, it's in the very center of the beam because of how our loads are applied. Okay, so that maximum vertical deflection is in the very center. And then same thing for the maximum bending stress. Okay, and then the experimental vertical deflection, you're just going to get that from the dial gauge directly. So there is no equation involved with that. You're just going to look down, read what that deflection is, and then put that down in your Excel sheet. So I'll bring this up to you once we actually do the lab next week, but the dial gauges that we have, unless we have new ones in the past, some of them are a little finicky sometimes. So that little nub or that indicator that touches the beam, sometimes it gets kind of stuck and it doesn't record anything. So when you start the test, make sure that you're looking at the dial gauge the whole time and make sure that's actually changing in value. If it's not, then you got to call Don over, the lab technician, and then he'll fix it for you. It's usually a pretty quick fix, but I think every time I've had this lab in person with these new dial gauges, there's always been like one or two that get stuck. Alright, so the last thing is the moment of inertia. So I'm going to draw the cross section for the I-beam. Okay, and as you can tell, kind of, it's not actually perfectly symmetric just because I'm a shit artist, right? But the sample that I give you in person, it's also not going to be perfectly symmetric. So what you're going to do, you're going to get that sample and you're going to take a lot of different measurements and you're going to take the average of them. So what I mean by that is you'll take a measurement for the base. So you're going to do that on the bottom, but also measure on the top. And then you're going to take the average. And same thing with the height. So you'll measure the height, let's say, on this side. And you can measure it in the center and measure it on the right hand side and take the average. And same thing with this dimension right here, S. You're going to measure that in a few different spots, take the average. And last thing, same with D, you're going to take the average. Okay, so you're going to get all of those, and then we'll get our formula that you're going to plug all of those values into. So what we have here is really, at least how I did it, is we have like 3 rectangles. So we have one big one. Okay, we have this big rectangle. So we're going to calculate the moment of inertia for that. So 1 divided by 12 times the base times the height cubed. And then we have 2 small rectangles, and we're going to subtract their moment of inertia. So these 2 small ones. All right, and what we get is 1 divided by 12 times the base times the height cubed, and then minus 2, 1 divided by 12 times s times d cubed. Let's just double check I wrote it down right. Yeah, okay. So that's going to be our formula for the moment of inertia for the I-beam. Okay, so do we have any questions on the lecture for today? Okay, let's see. Okay, yeah, so that's it for the lecture for today, but I want to finish off with a few reminders again. So make sure that you work on your memo, your first memo that's due today by 11:59 p.m. Your second memo is due next week. Remember that we had an exception for the first memo where I said that was due from 3 weeks from the date of the experiment, but all of the other experiments or memos, they're due 2 weeks after the date of the experiment. So Memo 2 is very similar to Memo 1. In fact, it's actually easier. There's less to do. So for Memo 2, the deliverables here, and the deliverables, they're kind of like a checklist for what should be in your report. So for Memo 2, we got to have a stress and strain curve. We're going to have 3 different figures because we had 3 different test runs. And each figure is going to have 2 curves on it. So one is the stress strain curve corresponding to the extensometer. The other is from the strain gauge. Then you're going to calculate the modulus of elasticity and compare that to published values. So you're going to be calculating that from, both methods. And then just the last thing that you have to do, and this will be in your discussion, you're going to discuss which method is most accurate and what the benefits and negatives are for each method. So, in practice, even though one might be more accurate than the other, in practice, you might prefer to use one over the other if they're both acceptable. I mean, it depends on your application, of course. And then the expected sample calculations, stress and strain, and the elastic modulus. And then I'll remind you one more time too, if you haven't come up with a team name yet, come up with that and tell me today so I can add that in Discord. All right, but that's going to be it for today. So if you guys have any questions, you can stick around. And remember that next week is going to be in person because we have an experiment. All right, so stick around if you have questions. If not, I'll see you guys next week and have a good weekend.